part A of this question, we need to find the minimum coefficient of friction, mu, such that the sphere will roll down the incline without slipping. So in order to solve this problem, we will need the use of forces. So our first step will be to draw a free body diagram for the sphere. So here's our sphere, and we know that there is a gravitational force, mg, and we know that there is going to be a normal force from the surface and a frictional force pointed up the incline. We can then split mg into components. So we know that this angle is going to be theta, if this is theta, and this component over here is going to be mg sine theta, and this one over here is going to be mg cosine theta. So we can first write our translational equations. So in our x direction, this is going to be the x direction, this is the y direction. Let us now look at the forces acting along both the y and the x directions. So along the y direction, we see that our object is not going to be accelerating anywhere. So we know that the sum of all forces in the y direction has to equal 0. So there are two forces acting along our y direction, the normal force and our component of our weight, mg cosine theta. So we can write n minus mg cosine theta is equal to 0. And solving for the normal force, we get that normal force is equal to mg cosine theta. Now let's take a look at our x direction. So our object is accelerating in our x direction, and so the sum of forces in our x direction is going to produce a translational acceleration. So sigma fx is going to be equal to m into a. So if we take a look at our free body diagram again, we see that there are two forces acting along our x direction. So we can write mg sine theta minus our force of friction is going to be equal to m to a. Now recall that the force of friction is always equal to mu, a coefficient of friction, times the normal force. So we can substitute our force of friction as mg sine theta minus our force of friction is going to be mu times our normal force, which is mg cosine theta. And this is going to be producing a force of m to a. We can divide by m on all the sides to get g sine theta minus mu g cosine theta is equal to a. And we can just clean things up a little bit by factorizing out our g. In order to get this. Now let's take a look at our rotational aspects. So the only force that is applying a torque on our sphere is going to be the frictional force. And if we assume that our radius of our sphere is r, we know from the rotational equivalent of Newton's second law that the sum of all torques will be equal to 0. Will be equal to the moment of inertia times the angular acceleration. So the only torque acting is the friction. So the only force that's producing the torque is the friction. So our sum of torques is going to be equal to r into the force of friction, which was mu mg cosine theta. And we know that the moment of inertia of a sphere is given by 2 over 5 mr squared. So we'll just write that here. And we also are assuming that our sphere over here is not slipping. And if the sphere is not slipping, we know that we're going to have our alpha, or our linear acceleration, will be equal to r into alpha. So alpha will be equal to a over r. So substituting that here, we're going to get this. Now we can clean things up a little bit. We can get rid of all our r's. We can get rid of our mass to get this as mu times g cosine theta is going to be equal to 2 over 5 into a. Now, we can substitute our expression for acceleration into this equation. So mu g cosine theta is going to be equal to 2 over 5 g times sine theta minus mu cosine theta. And since we're going to solve for mu, let us try to isolate it on one side. So we can expand and when we bring this to this side, we get 7 mu g cosine theta divided by 5 is equal to 2g sine theta over 5. So now we can cancel out our g's and our 5's. And finally, we can divide by 7 cosine theta to get our mu is going to be equal to 2 over 7 times tan theta. For the second part of our question, we need to do a little bit of an experimentation, and we need to figure out if mu is 0, whether the speed of the sphere at the bottom of the incline is going to be increasing, is going to be more, less, or the same as when it's rotating. So the first thing to notice in this question is that without our friction, our body, our sphere will never be able to rotate. And why is that? If you look at our diagram, we see that the force of friction is the only force that's producing a torque on this. So if the force of friction doesn't exist, then our body will never ever be able to rotate. So it's just going to slide down. So another thing to notice is that the initial energy of the object is the same, regardless of whether it's rotating or whether it is just sliding. That means by the conservation of energy, our final energy must also be the same in both the cases. So what we can notice is that when our object, our sphere, is just going to be sliding, our potential energy is converted into just a linear kinetic energy, and all of this energy is going to be converted into this. While for rotation, our mgh is going to be converted both into a linear energy with kinetic energy and a rotational kinetic energy. Now, in this situation, this potential energy can only give much less energy to this thing because it also needs to give energy for the rotation. As a result, this situation, when it is just sliding, will always be faster because more energy here is going to be transferred to our linear velocity. So the answer to this question is that the speed of the sphere when it reaches the bottom increases. And we can also show this mathematically to be true. So let us say that we release the sphere from a height of h. So we can use our conservation of energy, which states that delta U plus delta K is equal to 0. So in this case, our delta U, our final potential energy, is going to be, our initial potential energy is going to be mg into h. And our final potential energy is going to be 0. So our change in energy is negative mgh. Our initial kinetic energy in this case, where let's just say that the ball is rolling. So the kinetic energy in this case is our initial kinetic energy is 0, and our final kinetic energy is 1/2 mv squared plus 1/2 I omega squared. So we can bring this term to this side, and we get this. And now we can use the fact that the moment of inertia of a sphere is 2/5 mr squared, and we can use the fact that this object is still not slipping, so that means that our velocity is equal to the radius times the angular velocity, which means that our omega is going to be equal to v over r. So substituting all those in, we get 1/2 mv squared plus 1/2 times 2/5 mr squared times our v squared over r squared is equal to mgh. Our radius cancel out, our 2's cancel out, and we get 1/2 mv squared plus 1/5 mv squared, which when we add it is 7/10 mv squared is equal to mgh. Our m's cancel. And when we solve for v, we get v is equal to the square root of 10 gh over 7. And this is the velocity when our object is rotating. I'll be denoting that. I'll just denote that with this little small r over there. Now let's think about the situation where the object is just sliding. So again, even here in this case, we can use our conservation of energy. But the only difference in this case, like mentioned earlier, is that our potential energy is going to be mgh initially and 0 at the end. So our change in energy is negative mgh for potential. But the difference here is that the kinetic energy, while it is 0 at the beginning, the only thing that happens is it just gets converted to 1/2 mv squared by the end. So our change in kinetic energy is 1/2 mv squared. We can solve for our v by taking this term to the side. We cancel out the m's, and we get v is equal to the square root of 2gh for our translational. Now notice here that this is always going to be greater than this. So we have mathematically proved that when an object is sliding, its speed at the bottom of the incline will be more when there is no friction.